At Control Southeast, we have built a steam lab to help us better understand the movement of steam through a jacketed heating system. The successful operation of any steam jacketing requires the free flow of steam throughout the entire system and the efficient removal of condensate from the system. If condensate is allowed to collect in the jacketing, or if it prevents the flow of steam to the jacketing, this will reduce the steam's thermal performance and could result in processing issues. Our heating system features Contratrace bolt-on jacketing. There are 5 Contratrace heating elements attached to a section of 6-inch pipe. The heating elements are connected in series using flexible jumpers. A small boiler is used to produce 45-pound saturated steam. A steam supply line connects the boiler to the Contratrace, and a return line connects the Contratrace to an inverted bucket trap. In the field, pre-insulated tubing would typically be used for the supply and return lines, and flexible metal hoses would be used for the jumpers. But here we have chosen clear tubing so that we can see the flow of steam and condensate through the system. It is important to note that each jumper is looped downward below the outlet of the Contratrace. This orientation allows the condensate to freely drain out of the heating element. If the jumper had been looped upward, the entire heating element would fill with condensate, and steam would be prevented from contacting the entire surface area inside the jacket, and this would degrade the system's thermal performance. Condensate trickles out of the Contratrace into the jumper and collects at the bottom of the jumper. The condensate in the jumper does not prevent the steam from bubbling through and reaching the downstream heating elements. In the uphill side of the jumper, a vertical column of condensate continually forms, is disrupted by steam flowing through the jumper, and then reforms to repeat the cycle. The height of the water column creates a static pressure drop, which the steam must overcome to move through the jumper. A foot of water column represents a little less than half a psi in flow restriction, so the 45-pound steam has more than enough energy to overcome the water column and flow into the next Contratrace element. But the steam does lose some pressure in the process, and this pressure drop must be carefully considered in laying out the circuits in a steam jacketing system. Often, circuit lengths are dictated by conservative plant specifications, which limit circuit lengths to 1 or more pipe spools or to, say, 50 feet. This is a safe and effective approach, but it can also result in a more complex utilities infrastructure. By considering the pressure drop associated with each circuit, circuit lengths can be maximized to optimize the total utilities design. Each jacketed heating system ends with a steam trap, and the steam trap is generally the weakest point in the system. In this system, as a worst-case scenario, we position the trap at a higher elevation than the last element of Contratrace. This is not a recommended configuration, and most field installations feature the trap at an elevation below the jacketing. There are 3 basic types of steam traps: mechanical, thermodynamic, and thermostatic. In this system, we've used a mechanical type of trap. Our particular trap is an inverted bucket trap with continual air purging capability. As you can see, the trap works successfully in removing both condensate and air from the system. For more information on different types of steam traps, please go to the CSI University section on our website.